This video is all about what happens when an ionic compound is dissolved in water. Now, water, you may remember, looks like this. It's a bent molecule, and the electrons are more attracted to the oxygen than they are to the hydrogen. Now, water is not an ionic compound, but since the electrons spend more time with the oxygen and more time at this end of the molecule, there's what they call a partial charge here. This little symbol is a partial charge. It's a lowercase Greek d. And this end of the molecule is a partial positive charge. So not ionic, but charges anyway. And that has a lot of impact on chemistry, this idea of the partial charges. It's one of the reasons that water has a relatively high boiling point, for example, for its size and shape, because the water molecules attract each other. These aren't bonds in between the water molecules, but they're attractions. They're what they call intermolecular bonds. Bonds in between molecules. Not as strong as the covalent bonds between the H's and the O's, but an attraction. Now, when something ionic dissolves in water, the charges on the thing that dissolves are also attracted to these partial charges. For example, NaCl, salt, common table salt. As we all know, NaCl is really an Na plus ion and a Cl minus ion, and the bond here is an ionic bond. It's an attraction between that positive and that negative. Well, when something that dissolves in water gets into water, this positive guy is attracted to the negative end, or the partial negative end, of the water. And in fact, what happens is these guys actually separate. The water ends up surrounding the ions, with the positive end of the water surrounding the negative ion, and the positive ion being surrounded by the negative end of the water. That happens every time an ionic something dissolves. So when something dissolves, several things have to happen. One of the things that has to happen is the ionic thing has to break apart. And that takes some energy. But the idea of the water surrounding the ions, that actually gives stability to it. It actually makes up for some of the energy that got lost when the ions split up. Okay? So it's stabilizing to be surrounded by these charges, or these partial charges, these waters that are very polar. In things where the stabilizing effect of being surrounded by water, being solvated, that's called solvated, okay? That's this idea of being surrounded by water molecules. In things where the energy they get back by being solvated is more than the energy it took to break up, those are the things that dissolve in water. If it doesn't get the energy back to be solvated, they don't dissolve. That's why some things dissolve and some things don't dissolve. Now, Remember when we were writing equations? We could write something like Na3PO4 plus FeNO33 yields. Now this guy is aqueous, and this guy is aqueous. That is, they dissolve in water. Never mind how you know that at this point. I'll get to that in a minute. But just trust me, those guys are aqueous. They dissolve in water. Now if I'm predicting a property here, predicting a product here, the sodium goes with the nitrate, the iron goes with the phosphate, and I have NaNO3 plus FePO4. Now, let me just quickly balance there. Now, I also happen to know, again, never mind how at the moment, but let me just tell you that this guy is aqueous and this guy is a solid. Okay? Aqueous, 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 solid. Now, this guy is solid, again, because the solvation effects, this idea of this guy breaking apart and then being surrounded by water molecules, that idea of being surrounded by water molecules doesn't give it enough stability to make up for the fact that it broke up. So this guy does not dissolve in water. It's a solid. It sits at the bottom of your beaker, just like the sodium carbonate strontium chloride reaction you did in the lab. All right? Now remember that solid that was sitting on the bottom. This precipitation reaction. That's what that's called. A precipitation reaction. So you've mixed two aqueous things together, you end up with one aqueous thing and one solid. This solid guy is called a precipitate, and this is a precipitation reaction. And this way of writing a balanced chemical equation is a perfectly good way of writing a balanced chemical equation. But it doesn't accurately reflect this idea of things being in the beaker and dissolving and splitting up. So instead of writing this guy, we are actually going to write it a little differently. Anything that's aqueous, let me write the equation up here just so we have it. Na3PO4 plus FeNO33 yields NaNO3 plus FePO4. Okay. And this guy was the solid, this guy was aqueous, this guy was aqueous, and this guy was aqueous. Now, again, that's a balanced chemical equation. But we could also write something called the complete ionic equation that accurately reflects the idea that these guys are aqueous. In solution, it's not really Na3PO4. It's not really FeNO33. That's not what's really in the beaker. What's really in the beaker is 3 Na plus ions surrounded by water, hence the aqueous. And a PO4 3 minus ion, that is aqueous. And an Fe3 plus ion, that is aqueous. And 3 NO3 minuses that are aqueous. That's what's really in the beaker. You'll notice the polyatomic ions do not break up because they're covalently bonded. So they're not going to break up. Okay. But anyway, this is what's really in the beaker. All these ions floating about surrounded by water. Those are my reactants. At the end of this reaction, I still have 3 Na pluses that are floating about in the beaker. And I have 3 NO3 minuses that are floating about in the beaker. And I have my solid FePO4 that's sitting at the bottom of the beaker as a solid. It really is connected. It is not broken up into ions. So this is a much more accurate reflection of what's really in the beaker. Ions and the solid sitting at the bottom. That is a complete ionic equation. Now you will note some things here aren't actually changing. This sodium ion is just sitting there quietly floating about in the beaker and nothing ever happens to it. It just sits there, sitting in the water, sipping its drink, floating around, watching the action, but nothing happens to it. So I'm going to cross it out. I'm going to totally ignore it. It's not that it isn't still there. It is still there. I'm just ignoring it. This nitrate, same thing. It's still there, but I'm ignoring it. I'm not paying any attention to it. That's because these are called spectator ions. What are spectators? Spectators are things that watch and don't participate. So that's what they are. They're watching the action, but they don't precipitate. So what we're going to watch, or what we're going to write rather, is what's called, I'll choose another color here, the net ionic equation. And a net ionic equation is made up of the things that change in the course of the reaction. It does not put in the spectator ions. Fe3 plus PO4 minus yields FePO4 solid. Aqueous, aqueous. That is our net ionic equation. It does not include the things that do not change in the reaction. Now, mind you, again, they're still there. There's still sodium ions floating about and nitrate ions floating about. We're just ignoring them because they don't do anything in the course of the reaction. Now we got to answer this question of how do we know which things are aqueous and which things are not aqueous? And the answer is there's a table. Let's take a look at the table. Here it is on page 121 of your textbook. Solubility guidelines for common ionic compounds in water. Page 121, section 4.2. Compounds containing NO3- are always soluble. Compounds containing acetate, always soluble. Compounds containing Cl-, always soluble, unless you're talking about silver, this dimercury ion, or lead 2+. Ditto Cl-, Br-, I-. Those halogens all have the same solubility and exceptions. Sulfate, almost always soluble, except for these guys. Now, things containing sulfide, carbonate, phosphate, hydroxide, those things are almost always insoluble. Except, and once again, this is really kind of important. Look at the exceptions. Alkali metal cations and ammonium. Basically, +1 ions, they're almost always soluble. No matter what these guys are, they're almost always soluble. That's why in the reaction, I picked sodium phosphate because I knew that would be soluble because it had sodium in it. And iron nitrate, I knew that would be soluble because nitrates are always soluble. Sodium things, potassium things, +1 ion things, always soluble. Nitrates, always soluble. But phosphates, for the most part, are not soluble unless it's a +1 ion. So iron phosphate precipitated out. Okay? So, be familiar with this chart. You do not have to memorize this chart. I will give you the chart. But be familiar with the chart. Understand the chart. Know how to read the chart. And there are other kinds of net ionic reactions. There are other kinds of net ionic equations. But let's stick with precipitates right now. In general, the only thing you need to remember is anything that changes in the course of the reaction, that's what you write in a net ionic. And things won't change if they're ions at the beginning and they're ions at the end.